3.
All right, another little bit of motion in 2 dimensions, which can be extended to 3, kinematics 2 dimensions, is relative motion. It's often called Galilean relativity, as opposed to Einstein's relativity or special relativity, which kind of builds on this but goes pretty wacky pretty fast. This is intuitive. This makes sense. So I've got 3 examples here, really 2. Walking on a boat, flying in the wind. You could think of rowing a boat in moving water as well. And you just have to get a sense. If you know your vectors, you're fine. I mean, ultimately, if you want to analyze what happens, we go back over here. You know, the definitions for motion, kinematics, describing motion, velocities, rate of change of position, written as derivative or integral, accelerations, rate of change of velocity, x direction, y direction, if the acceleration is constant, fine. So that's how you analyze it. But how do you relate these velocities? For example, if the boat's going 10 miles an hour and you're walking with it 3 miles an hour, which is kind of standard walking speed, then relative to the ground sees the boat going 10 miles an hour, but it sees you moving up toward the front. So relative to the ground, it sees you walking 13 miles an hour relative to the ground. The boat's moving 10, you're moving 3 in the boat, so it's the combination. If you go backwards, then relative to the ground, you're going 10 minus 3, or relative to the ground, 7 miles an hour. If you started here and the boat was going 3 miles an hour that way, and you walk 3 miles an hour that way, relative to the ground, you'd stay in one place. If the boat goes that way, you'd go towards the back. You can try that on a train, like a BART train or commuter train or anything like that, or a bus. It's kind of fun. But how do we deal with it if it's 2-dimensional? The notation works really well. Flying in the wind. It's the same kind of thing. Your plane can travel a certain speed, but the wind will carry it one way or another. It can go whatever direction. So if there was no wind, your plane would travel at a certain velocity relative to the ground. But the wind will either add or subtract velocity in each of the directions. So that's a great thing. This is a good example of how wise, careful, good notation will lead you to write the relationship. I mean, you know kind of what's going on, but it'll let you analyze it and work with it. Check this out. This is great. Okay, suppose I want to know how fast you're moving relative to the ground. All right. So that's the velocity of you relative to the ground. Now, some people write this different ways, but I like this notation. You could write it like this, slash, it doesn't matter, sometimes a comma, but this is really nice. The velocity of you as seen by the ground. Now it's 2-dimensional, so I can write it, you know, x component, y component, or I can just use that symbol and say, okay, I could rewrite that as the x motion and the y motion separately. So there it is. The velocity of you relative to the ground is equal to the velocity of you relative to the boat, how fast you're walking as seen by people sitting on the boat, plus the velocity of the boat relative to the ground. Now that notation is so cool, because what does it do? Well, you kind of look like VUG is VUBBG. It's like the B's go away, and there you have it. So you just write that, and then look back and see what it is. Again, you can write this x components, and then y components if you want. Whatever. The neat thing here is you can subtract too. So the minute I write that, and how do I know I've got it right? Because just by the order of the subscripts, UG, UB, BG. So that means I could write VBG is equal to VUG minus VUB. Because I just rearranged it, and then I get it right. So however it goes. We'll explore that in just a minute too. So how do I do that for a plane flying in the wind? It's the same thing. So here I'm leaning a little more on my math and my notation. I know what's going to get me right. So I've got, let's see, the velocity, x component, separate from y, whatever, but combined here, the velocity of the plane relative to the ground, how much progress is it making, right, is equal to the velocity of the plane relative to the wind. I just used my notes. PG is PW plus VWG, and the W's kind of go in there. If you think about it, it's true. Just think about walking with the boat, opposite the boat, flying with the wind, opposite the wind. And that applies in 2 dimensions and 3 dimensions. So then I can rearrange it however I want. So in general, we have this. Now let's think about this last little bit. So if you just start with that, you're good. The idea is just, again, walking with or against the boat in the x direction, and then you can think of it in the y direction. Fine. VAB equals negative BBA. That's important to realize. If I'm walking this way, 3 miles an hour, you appear to be moving the other way. The velocity of me relative to you is the opposite direction of the velocity of you relative to me. That's all. So that's kind of neat. Watch what I get to do up here. Let me go back here. This means that the negative velocity of you relative to the boat is the positive velocity of the boat relative to you. And that's the velocity of you relative to that. So I could do that. Wait a minute. I could play, I'm totally forgetting what I'm talking about. Notation here. Wait, that's the velocity of the boat relative to you, plus the velocity of you relative to the ground. Wait a minute. There's the subscripts here. That's the velocity of the boat relative to the ground. See how they go? Hey, it is. It worked. And so the power of good notation really comes out when you do relative motion. The power of setting things up with good subscripts, it can really guide your thinking as you get into processes that are just too hard to think of all the factors involved. Okay, so relative motion doesn't have to be too bad, and then you put in your particulars. You do the x part, and then you do the y part separately. And you have this general thing. I mean, velocity of A relative to C is the velocity of A relative to B plus the velocity of B relative to C. And then you can move them around, and you know you can always flip the sign and rearrange, and you're good. You're set up. So just use that. We're not going to do too complex things, but this prepares you for some later work. Think about it. Walk on a train and notice it, and you're good.